When we've been differentiating, we've looked at lots of different types of functions, some of them quite complicated where we've had to prepare before we differentiate, but we've always been using the basic rules: multiply by the power and reduce the power by 1. Sometimes we're going to have to differentiate expressions which involve trig functions, and we can't use that rule. So we have other rules for this. We're not going to be doing a proof for those today. I'm just going to tell you what the rules are. If we differentiate a sine of something, we get cos. And if we differentiate cos, we get negative sin x. You're going to want to remember these. Something like this is available in the formula sheet, but it's not quite in this form, and it's just easier if you remember. So the derivative with respect to x of sin x is cos x, and the derivative with respect to x of cos x is negative sin x. So our first example on page 19 is y equals 3 sin x, and we're asked to differentiate with respect to x. So dy by dx is equal to, and we know that if we differentiate sin x we get cos x, so if we differentiate 3 sin x we're going to get 3 cos x. It's important to remember that when we're differentiating trig functions we need to be working in radians and not degrees. In our next example that's going to become a little bit more important. We're given a function sin x minus 2 cos x, and we're asked to find f dashed pi over 3. So we're going to find f dashed x first of all, and then we're going to substitute in pi over 3. This is a rate of change question. So we're differentiating. Trig functions are the same in that we can differentiate sums. So I've got sin x minus 2 cos x. So I can just differentiate each of them in turn. So sin x differentiates to cos x. Cos x differentiates to minus sin x. So that minus 2 is going to become a plus 2, not a 3. And it's going to be sin x. So f dashed x is equal to cos x plus 2 sin x. So f dashed pi over 3 is going to be equal to cos pi over 3 plus 2 sin pi over 3. Now to evaluate the cosine and sine of pi over 3, I'm going to remind myself using my exact value triangle. So I'm using the triangle that was an equilateral that's been chopped in half. So the hypotenuse is still 2, the bottom is 1, and using Pythagoras the other one must be square root of 3. It was equilateral, so all of the angles were 60. This one remains 60, this one's been chopped in half, so it's 30. We're thinking in radians. Pi over 3, pi is 180 degrees, so pi over 3 is the same as 60 degrees. The cosine of 60 degrees, if you've forgotten from last year, cosine is adjacent over hypotenuse, and it's the cosine of 60 degrees that I want. So adjacent to the 60 degrees is 1, and hypotenuse is 2. So the cos of pi over 3 is 1/2. And then I've got 2 times the sine of pi over 3. And the sine of 60 is opposite over hypotenuse. Opposite is pi over 3, and hypotenuse is 2. So it's 2 times pi over 3 over 2. These 2's are going to cancel out, so I have 1/2 plus pi over 3. Okay, and the third example, we're asked to find the equation of the tangent to the curve. So the tangent's a straight line. To find that equation, I'm going to need a gradient and a point. Now I've been given an x coordinate, so I can use my function to work out the y coordinate. So that will give me the point. Then I need a gradient. To get the gradient, I'm going to differentiate, because that gives me an expression for the gradient. I'll substitute in the x value, and then I'll be able to use y minus b equals mx minus a. So firstly, let's find that y coordinate. So x is pi over 6, y is the sine of x, so it's the sine of pi over 6. Again, we need to look at our exact value triangles. And it's the same triangle we used the last time. Pi over 6, remember pi is 180 degrees, so pi over 6 is the same as 30 degrees. On this triangle, it's the equilateral that was chopped in half. So hypotenuse is 2, 1 on the bottom. Pythagoras tells us that one will be root 3. 60 in the angle that remained the same, and 30 for the one that was chopped in half. And we also need to remember SOHCAHTOA so that we know which sides we're looking at. So the sine of 30 degrees, sine is opposite over hypotenuse. Opposite is 1, hypotenuse is 2, so that's 1/2. So the point that we have is pi over 6, 1/2. We've got a point, so now we need to find the gradient. Y is equal to the sine of x, so dy by dx is going to be equal to the cos of x. Our gradient is going to be equal to the cos of pi over 6. And we use our exact value triangle again, so the cosine is adjacent over hypotenuse. It's 30 degrees. Adjacent to that is pi is square root of 3, and hypotenuse is 2. So our gradient is root 3 over 2. So we'll bring those together to work out the equation of the line. So y minus b is mx minus a, and I'm putting in a gradient of root 3 over 2. Having a is pi over 6, and b is 1/2. So I have y minus 1/2 equals the square root of 3 over 2 times x minus pi over 6. Now I'm going to multiply everything by 2 so that I can get rid of this fraction. So 2y minus 1 equals root 3 times x minus root 3 times pi over 6. So I'm just going to move everything to one side, tidy it up slightly. So root 3x minus 2y minus root 3 pi over 6 plus 1 is equal to 0. And that's as tidy as we can get this one, really. So we're just going to leave it as that. Okay, so I just want to check that you have remembered what we've done. So what's the derivative of cosx? And can you draw your exact value triangles from memory? Knowing that the derivative of cosx and the derivative of sinx is only a very small part of this. The exact value triangles, understanding radians versus degrees, being confident using surds and radian measures are going to be all the things that are going to help you with this exercise. We're now ready to move on to exercise 14b. Question 1 and 2 are unit level. Question 3 and 4 are level C. And question 5 and 6 are AB. If you are not confident with exact values or radians, please take the time now to go back over those.